Hello all, I welcome you all to the 19th lecture in this course EE 698M, lecture 19. So last time or the previous few lectures we spoke about electron interactions with charged particles. We saw electron interactions with phonons, how they get scattered and so on. We saw about the Fermi's golden rule. One has to remember that the Fermi's golden rule was not identified by Fermi but then by Dirac, but then Fermi called it golden rule because this is what determines scattering, how electrons behave in many places, right? So it's called the Fermi's golden rule, which gave you the probability of scattering between any two states, right, depending upon the overlap integrals between the initial and the final state with the perturbation. That's what Fermi golden rule eventually tells. I want you to go back and take a look at it. So today we will discuss a little bit in more detail about the optical properties. Why is this important? Firstly, electromagnetic radiations. Optics is basically electromagnetic radiations, right? Electromagnetic radiations affect electron populations in a material, right? It can excite, or an excited particle can radiate and come down. It will affect the electron population. And second, the electromagnetic radiations ranging from few milli electron volts, the energies are determined in few milli electron volts, to all the way to 6 electron volts can be used to study about the various physical properties of materials. What do we mean by physical properties? Like its density of states, band gap, electron population, right? So on and so forth. We will see very soon how those things are determined by electromagnetic radiation as the interactions. So as we saw previously, let's say we have an interface. On the left hand side we have pure vacuum, nothing, and then we have some material, and typically the material is determined by some dielectric function, right? We call it epsilon r or whatever. The vacuum permittivity is epsilon naught, right? So this is epsilon naught, epsilon r, the total epsilon. These are some things which are called as macroscopic electrodynamics. We don't go into details about how the electrons in each of these material interact with the radiation. We just know on an average how things work. These are like the thermodynamics, right? So it's called, firstly we will talk about the macroscopic electrodynamics. So let's say that we have some radiation which is incident on this material. There are a few things which can happen. It can be scattered back, it's called as reflection. It can be transmitted forward. As it is getting transmitted forward, there can be some absorption, there cannot be any absorption. I mean, there need not be absorption, so it's transmitted, right? The scattered light, so in the transmitter there is no change in wavelength, right? So in the reflection also there is no change in wavelength. It can be scattered such that its wavelength, its energy of single photons are being changed. There are two ways in which it can be scattered. One is called as Raman scattering, another one is called as Bullion scattering. What is Raman scattering? We will see all these things in a minute, okay? And it can actually emit a radiation. So whatever, so you send in some light, it can emit some radiation. It's called as luminescence. I hope you must have seen photoluminescence and such things, right? So you shine some light and you have some luminescence. That light can be entirely transmitted or being absorbed. And this can happen mostly in the case of metals, right? The light gets completely absorbed when the metal is thick enough. If the metal is very small, it just gets transmitted. A portion gets transmitted. You have Raman scattering and you have Bullion scattering. We will just talk about what is Bullion scattering. Or it can be reflected back. And you know what is the angle at which it is getting reflected. This is Snell's law. The angle in which it gets transmitted. All these things are very well known. right? So among the various processes, the most dominant process is reflection and transmission including some absorption, right? These are the most dominant because they are the first order processes. What do you mean by first order process is that you need to involve no other particle. You have some particle or you have some energy which is a wave which is coming in, it gets scattered out as a different wave, different direction, whether it is being transmitted, forward, reflected, but there is no another particle which comes into play, right? In the second way in which this can be scattered, where it requires assistances from different other materials, different other species, you have what is called as scattering. Let's talk about Raman scattering. What is about Raman scattering is that you have a light which is getting scattered, but now it uses another elementary particle which is called optical phonons. So scattering, so basically let's say we have a photon which is coming in and it gets assistance from another phonon. So this is Q optical. Remember, in the phonons there are two kinds of branches, the optical branch and the acoustic branch. The optical branch has higher frequency, higher energies, and the acoustic branch obviously has lower energies, right? It has to do with how the molecules vibrate, whether they vibrate in phase, they vibrate out of phase. So let's say you have something which is coming in K and got scattered out as K prime. Here your photon can either be absorbed or your phonon can either be absorbed or ejected. That's where you can get what is called as Stokes and anti-Stokes in Raman scattering, right? So this is called Raman scattering. The third way is called the Bullion scattering. It is the same process where instead of an optical phonon, you have an acoustic phonon. Again, you have the same kind of thing. You have an acoustic. So what does acoustic mean? Just have low energy, right? So K and K prime are now much smaller, much closer. Alright. So these are the various processes that can happen, and the fourth one is called as photoluminescence. I'm not sure if you guys would have seen it. So what happens is, let's say we have a band something like this, and you shine a light whose energy is much larger than the band gap, h cross nu larger than Eg. Under such situations, you have electrons in different places getting excited to much higher energy levels, right? Under such situations, these guys can come down, they scatter down from here to here, and they recombine, and as they recombine, they emit light. So what happens? So when you draw the emitted light intensity versus wavelength lambda, you will see that it behaves something like this. So this is what is called as band edge absorption. This is because you see that smaller band, smaller energy, smaller wavelengths are higher energies, right? So this Eg corresponds to the band edge of this semiconductor that we are talking about. So we will not deal a lot with this, but then yeah. So let's talk a little bit about macroscopic electrodynamics. We started talking about this in the previous lecture. Let's say that we have an light incident on a material which is expressed by like this form: E naught e power I k dot r minus omega t. So obviously this is a traveling wave with wavelength wave vector k and the frequency omega, right? It has this energy h cross omega. These things are pretty well known to you by now. Now this electric field will induce a polarization. So induced polarization in the material is given by P. Note that this P now will not be direction independent. It has some direction. Let's say in a three-dimensional world, it is given as Pi r dash comma t dash is given by x chi, which is called as the electric susceptibility tensor. It has this form. It is proportional. It has a function of the light wave vector k and its frequency into Ej r comma t dr dt. So this is more or less like a convolution function, right? So basically, let's say this x will be let's say 3 by 3 tensor, and this is let's say 3 by 1 vector, right? In 3 dimension, the electric field with 3 by 1 vector, you will finally get a 3 by 1 vector, which will be the polarization in different directions, right? So this is what is called as the polarization. What do we mean by polarization is, let's say that I have a material like this, and then on this there is an incident electromagnetic wave where its electric field is polarized in this direction, normal to the way in which it is propagating, right? So the arrow shows the direction in which it is propagating. There are two ways the electric field can be polarized, right? It can be, obviously, electric field is perpendicular to the direction of propagation. This is how electromagnetic radiations are defined, right? If something is going like this, you have two directions in which it can be perpendicular. It can be, electric field can be polarized. Either it is in this fashion or the other one which goes normal to your screen, right? In this fashion. There are two kinds of polarization. When it is like something like this, now the electric field gets accumulated either, let's say, in this fashion, or it goes, let's say, positive, negative, depending upon the way in which electric field lines are oriented, right? Now the electric field, the light will have different velocities along different directions of this material, which will give you this tensor, which when acting on this electric field, which is a 3 by 1 vector, will give you a 3 by 1 polarization vector, right? Don't be worried about all these big matrices and these tensors, because in most of the cases we are going to talk, or at least in this course, we will not assume any anisotropy. We will assume all of them to be isotropic. Under these situations, this tensor can be decomposed into a scalar function. So what we typically write is the polarization P is written as some dielectric susceptibility function x into the electric field E. The dielectric displacement vector. The dielectric displacement vector gives you the charge separation due to the applied electric field E plus the polarization that the electric field has induced in the material, right? So basically what happens, you have this material and then you shine the electric field. This will give you some polarization P and the electric field itself in the material causing some displacement, that is some dielectric displacement, right? So this is what is called as the dielectric displacement, which can of course be written as epsilon naught E plus 4 pi epsilon naught chi into E, which is totally written as chi into E, where this epsilon is epsilon naught into 1 plus 4 pi chi naught, right? and this epsilon is called as dielectric function. As I said before, this dielectric function in any generic material would be a tensor function, right? Because this chi naught is a tensor, and because this chi naught is a tensor, this epsilon dielectric function will also be a tensor. But in an isotropic material, you will assume it to be a scalar function. In our previous discussions, the velocity of light in a material is given by the velocity of light in free space divided by the dielectric function power 1 by 2. And because, as we saw previously, this dielectric function is not in a generic material, it does not have to be uniform. So it's a tensor with two variables, right, I and j. Under these situations, you can have some, let us say, if the velocity of light in a material is different under different directions, it is called as birefringent. If it's isotropic, then it is called as biaxial material, but you don't have to know about it. So if the velocity of light is different along different directions, you call it the birefringent material, and which is useful in certain cases of optics where you start to work with nonlinearity like Kerr rotation and so on and so forth, right? So alright, so now we have defined the dielectric function. One last thing that we have to know to work with the dielectric function is that the dielectric function is complex. So this epsilon is typically written as epsilon prime plus I epsilon double prime. Epsilon prime is the real part of the dielectric function, and epsilon double prime is the imaginary part of the dielectric function, and these two are related by the Kramer-Kronig relation, right? So epsilon prime is given by 1 plus 2 by pi some Cauchy integral w prime epsilon double prime. This is the imaginary part of omega prime, the omega prime, divided by omega prime square minus omega square. This is like this. Epsilon double prime of omega is given by minus 2 omega by pi Cauchy's epsilon. This is the real part of omega prime d omega prime by omega prime square minus omega square. So what people typically do is you can obtain the absorption coefficient by studying something. Let's say you take a material and then you shine a white light and then see what is the absorption. Then you get the imaginary part of the dielectric function. Once that is given, you get the real part of the dielectric function by the Kramer-Kronig relationship, right? So now that we have seen about the macroscopic properties, let us go into what we actually should discuss today, which is the microscopic picture. That is what we are interested, because we wanted to see how the electromagnetic radiations interact with electrons in a material. So let's take initially a material in which there is no light interaction, and we know the Hamiltonian can be written as H naught is P square by 2m plus some V of R. This is the standard Hamiltonian for an electron, right? And for electromagnetic interactions, we are going to assume various gauges. I suppose you remember what is a gauge, because that is to do with the solutions for electromagnetic radiations. The first thing you take is, because del dot B equal to 0, because the magnetic field does not diverge, you start to take A as some magnetic potential such that B can be written as del cross A, and because of the way in which the operators work, there are different solutions. A need not be necessarily unique. So the gauge that we take is to define how A can be taken. We take what is called as Coulomb gauge to discuss electromagnetic interactions. Under this gauge, what we do is we take del dot A to be 0 and the potential, electric potential psi to be taken to be 0. Okay, this is the definition of the Coulomb's gauge. Now, to discuss electromagnetic interactions with a material, what we do is you convert the momentum operator, that is P, which is basically h by I del, is converted to h by I del plus E into A. Now, I want you guys to take it that this is true, right? For you to prove this, we have to dig a little bit deeper into classical mechanics, which we will skip for now. So take it for like a formula, like the momentum of an electron in the presence of an electromagnetic radiation is given by h by I into delta plus E into A. It is like saying that the kinetic energy is half mv square, right? Nobody asked me why it has to be half mv square. So it's like Newton's laws. It can be proven, but it can be proven in a very roundabout way. So like that, the momentum of an electron in the presence of electromagnetic radiations with the magnetic potential given by A is written by h by I delta plus E. With this given, I'm going to denote this as P dash. With this given, let's take the Hamiltonian H, as we wrote previously, is given by 1 by 2m P dash square plus V of R, and which can be written by 1 by 2m into P plus EA square plus V of R, which is H naught plus EA P dot EA by 2m, right, plus EA dot P by 2m plus E square A square by 2m. And if we take A to be small, if we take the light intensity to be small, then A square will be much smaller. So we are going to make this to be 0, and we are left with H naught plus 1 by 2m into P dot EA plus EA dot P. And let's just take one of them and then see how to reduce this. So P dot A, let's say P dot A acting on some function is given by P is h by h cross by I into delta, right, dot A acting on some F. Now you have to use the product rule, which will be given by h by I del F dot A plus del dot A into F, right? And you know that del dot A is 0, right? This is the Coulomb's gauge. We write del dot A to be 0. So this turns out to be 0. So what will be left is h by I into del into F dot A. So this is basically A dot del acting on F, h by I, right, which is A dot P acting on F. So P dot A acting on F is given by A dot P acting on F. So which will give both of them to be the same, which will eventually give h naught plus 1 by m E P dot A. And this is h, and because we have taken A to be small, we can treat this perturbatively, and we denote this small one to be h prime, right? Now let's look at the perturbative solution for, so what did we do till now? We have taken a material and then we are trying to see what should be the Hamiltonian when we have electromagnetic interaction when you have electromagnetic interaction with these electrons in this material, right? And what will be, how we are going to solve this? We are going to use the time dependent perturbation theory, and we will follow the same line of treatment that we did when we did the Fermi's golden rule derivation. So what did we take? We assume that the interaction is weak. Interaction is weak. It does not affect the eigenfunctions, and all that it changes is the relative contribution. So let's say psi naught is given by some summation C naught psi I, right? And psi of t is just given by summation C n of t psi n, right? So in the presence of perturbation, all that changes are these coefficients. The wave functions do not change, the eigenfunctions do not change. This is the basic assumption of time dependent perturbation theory. This comes about because you assume that the electromagnetic radiations is weak. Under this situation, we actually derived this time dependent perturbation theory previously, so I'm just going to use the result. Cn of t is basically given by minus I by h cross integral 0 to t, and the summation of overlap integrals. Some, let's say, we are talking about the nth coefficient, right? This is summation over all i's h prime, that is the strength of the interaction working on psi I. This is the ith summation, and of course we are talking about time dependent, so we are going to have e power minus I en minus ei into t by h cross, right? So now, as we saw previously, h prime is what is h prime? 1 by m e by m p dot a. It's e by m p dot a, and I'm going to take a to be electromagnetic radiation, which is sinusoidal, right? So I'm going to take a as some e naught e power I k dot r minus omega t. This is the forward propagating wave, so plus its complex conjugate. This is how it is written in quantum field theory in many of the solid state physics. We write c dot c for complex conjugate, because what we will eventually have here is, let's say, another term e power minus I k dot r minus omega t. So it's just a short form. You will see why this is useful. Okay, we are going to make some other simplifications just to get rid of this large summation and some important reductions here. First simplification that we are going to use is, let us take only two levels. So let's say, as we saw previously, let's say we have two levels. We say the initial level and the final level, and we have a light A which is getting in, which wants to interact between this initial and final levels, right? And let's say this separation in energy is h cross omega naught, and the energy of the incoming light is h cross omega, right? These are the assumptions that we are going to start with. The second one I will discuss in some time. This is the first assumption. So let's go back to this equation. Because there are only two levels, there is no summation. N will be the final one and I being the initial one. So basically C final of t will be given by minus I by h cross integral 0 to t. There is no summation. Y final H cross is basically E by M P dot A psi initial into e power minus I. So this is omega, right? En is so this is omega naught t. So now let me substitute A to this minus I by H cross integral 0 to t. Remember, this overlap integral is just a spatial overlap, right? So it is an integral psi f star E by M. P is, let's say, H cross by I into delta dot. E is E naught e power I k dot r, remember, plus e power minus I k dot r, right? So this is what I mean when I say I'm going to write it just by complex conjugate. I'm going to remove this. You will see that, right? And the time component, so this is the spatial component. This is minus infinity to plus infinity into psi I dr, and the time component of this will come. Time component of this is e power minus I omega naught t into this guy is just e power I omega t, right? Into e power I omega t dt. All these things plus its complex conjugate. So what will turn out? It will be minus I by H cross integral 0 to t. I am going to write this expression. So this is psi f star E by M. I am going to take E by M out. E by M H cross by I out. E naught also out. Minus infinity to plus infinity. Psi f star into del e power I k dot r psi I dr, right? So basically this is an overlap integral. This is what they call as the selection criteria, right? So I'm not going to evaluate this. I'm going to substitute this as something else for now. Into, on the other side, e power minus I omega naught minus omega t plus its complex conjugate. Now I come up with the second simplification, which is called as electric dipole approximation. It says that the light wave vector is much larger than the electron wave function, electron wave packet. Remember, these psi f's and psi i's are block waves. Block waves are electron wave packets. So if you assume the wave packets to be much smaller in comparison to the size of the wavelength of the electron, then you can actually e power I k dot r. So what we mean is the k is much smaller than r, right? So basically k dot r is a much small value, is a very small value. If it's a very small value, obviously the exponential can be e power ikx. It's a very small value. So e power I k dot r can be basically approximated to be 1. So in this expression, you just e power I k dot r is just 1. So what will turn out will be minus I by h cross integral 0 to t e by m h by I e naught integral minus infinity to infinity psi f star delta psi I dr into e power minus I omega naught minus omega into t plus its complex conjugate. Now we can take out things which does not have any time dependence. So I am going to let me write this entire thing as some s, right, and the i's will go. So finally what we will have is minus s by h cross integral 0 to t e power minus I omega naught minus omega t plus the complex conjugate of this part, which will turn out to be e power I omega naught plus omega t into dt, and integration of this will be minus s by h cross e power minus I omega naught minus omega t divided by omega naught minus omega. I am going to take the I out, so instead of minus I will get plus I here, plus minus 1, right, because 0 to t, so this will come minus 1 plus e power I omega naught plus omega t minus 1 divided by omega naught plus omega. This is C final of t. Now obviously we are looking at situations when omega is the frequency of the incident wave and omega naught is the energy difference between the initial and the final energy levels, right? So this is what we are talking about. Omega is the frequency of the incident radiation, omega naught is the difference in energy levels. So we are looking at situations where omega is almost close to omega naught, right, something in the small band. Under such situations you can easily see that omega naught plus omega will be much larger than omega naught minus omega, right, magnitude wise. So the second term, where it comes in denominator, will be much smaller than the first term. So Cf of t will be I s by h cross e power minus I omega naught minus omega t minus 1 by omega naught minus omega. And obviously this can be written as I by h cross e power minus I omega naught minus omega t by 2 divided by omega naught minus omega, and this will give out 2 sine omega naught minus omega t, right? So sine omega naught minus omega t by omega naught minus omega is a sinc function, and you know how this will work, right? So if you plot it against omega, when it is omega naught, you will have something like this. This is Cf of t, and the probability for the state to go from initial to final is given by mod Cf of t square, which is 4 s square by h bar square sine square omega naught minus omega t by omega naught minus omega square. Now when t tending to infinity, this sine square by the sinc square will look almost like a Dirac delta. So the probability, the rate of transition will turn out to be 2 pi s square. This s square is the overlap function square, I hope you remember, delta of omega naught minus omega into t. So which means that if I have two states, this is the initial state and this is the final state, and I have an incident radiation omega and the separation is omega naught, right? The transition is, you will transit from the ground state to the initial state to the final state, which will be the same as final to initial as well. I think this is what we saw previously also in the Fermi's golden rule. There is the transition probability does not change when we change the initial and the final state. When we swap the initial and the final state, the transition probability does not change, right? Under such situations, you see that this light will create with equal probability an excitation of an electron from the valence band to the conduction band, which is called as absorption, and with the same probability it will also do what is called as a stimulated emission. So let's say that we have an electron already lying here, and if this system is perturbed by a frequency omega, this will ensure that this electron will come down from here to from the conduction band to the valence band, final to the initial state. Of course it should be reversed in the other way, but now instead of one photon, now you will have two photons, right? You have the photon which caused this transition, and because this transition has happened, it will give you another photon. As you can clearly see, this is what is called a stimulated emission. Why it is called a stimulated emission? You have to remember, you have to start with an electron in the final state, in the excited state. Under that situation, if you perturb this system with a photon, this will induce a transition from the excited state to the ground state by emitting a light. Now you have two photons which are in phase, and these two photons can once again trigger multiple recombinations, right? If let us say what you have, what is called as a population inversion, this is what is done in a laser diode. You have stimulated emission because of this photon. You have this one photon giving you, let's say, four of them now, right? Because let's say this photon will give you one recombination, this photon will give you a second recombination. By the end of these two, you will have four photons here, right? Two coming and then this, and this will grow in an exponential way. This will finally give you a highly coherent light source from a semiconducting device. This is what is being used in a laser. Now these two are easily understood. There is something which is not too obvious, which is called as spontaneous emission. What we mean is, let's say you have an electron in the excited state. This is the final state and this is the initial state. Now even in the absence of a photon, even one single photon, you have what is called as a photonic vacuum. Even in the photonic vacuum, you know the energy is not zero but half h cross omega, right? So basically you have some fluctuations in photon numbers which will eventually give you zero. Under such situations, it is possible that an electron can be stimulated to emit from here to the ground state, giving you a photon out even when you have a photonic vacuum. This is because of vacuum fluctuations in the photonic ground state. You have what is called as a spontaneous emission. Because you have a photonic vacuum, the final state has only one photon, which can be contrasted with a stimulated emission where the final state will have two photons. right? So this is something which is used quite extensively in many practical applications like light emitting diodes, lasers, and so on and so forth, right? So with this we will stop our discussions on electron photon interactions. We will do one more lecture regarding photons and states, that is excitons, and we will stop our discussions, and then we will go to the last part of this course, which will be superconductivity. Thank you.